Okay. Good morning again. This is MMI711 sequence models in multimedia. And this is week 10. We're going to talk about transformers and specifically about vision transformers. But before I start this subject, let me make a few announcements. Now, I've already said that it's week 10 and we're about, I see this week as the week that we kind of enter the last part of the course, because in this course we are going to spend the last 2 weeks for your presentations. Soon I'm going to announce who's going to present in week 13 and who's going to present in week 14. Then, which means we have only 3 lectures. I'm counting this one, 3 lectures left. And what I usually do is, for the last lectures, like 2 lectures, I kind of lower the intensity of the lectures. I have lesser number of slides. I cover, less volume of things to tell, because towards the end of the course, usually students lose their focus and they have their projects going on, which is like the 40% of the course. So it's kind of, as you get closer to the end, you kind of get slower. So I'll try to catch up with your speed. So that's why we're going to cover transformers only today, which is also already a very, complicated subject, but we are ready to cover it. And other than that, we got 2 weeks. We are going to cover RNN trackers next week, and the other week we are going to cover our final subjects, and the last 2 weeks will be your presentations. And nothing else. There's the homework you're doing until the end of this month. So that's all about administrative stuff. And this week is all about transformers. So before I begin, let me show you a article I've seen recently. This is very new. This is 3rd of November, 2002, but not 2012, last year's. It's a interview with Jeffrey Hinton, and it is kind of the date is important because the subject we are going to cover, the vision transformers, was almost the same days this interview was held. However, this interview will refer to the original transformer paper, which is 2017. But before we get to transformers, let me tell you why I am talking about this article. They ask the godfather of deep learning, do you think what deep learning will be able to do in the future? And he says deep learning will be able to do almost everything. What he says is almost everything humans can do, because I don't know what is beyond what humans can do. It kind of sounds like science fiction. And when they ask how it's going to do it, how are we going to get there? If you're going to replicate, you think deep learning will be enough to replicate all human intelligence? What makes you so sure? When they ask, he answers exactly, I think there's going to be quite a few conceptual breakthroughs. So he believes that there will be some breakthrough steps that we're going to have to take, quite a few, like 10 or 20, I don't know. And he gives an example. For example, in 2017, Vasvani et al. Introduced the transformers, which drive really good vectors representing word meanings. And I love the thing about this guy. When he's talking about papers, he doesn't necessarily name the title or the subject. He exactly touches the point what the paper did or had a contribution. And actually it was transformers contribution, good vectors representing word meanings. So I believe you have taken an introductory level deep learning course before this one. You've seen AlexNet, the convolutional neural networks. That was a breakthrough. Then we had minor breakthroughs in convolutional neural network stuff like YOLO and etc. Then using LSTMs with CNNs was also a breakthrough. LSTMs was a breakthrough itself. Then transformer, which we are going to cover today, is another breakthrough. And as if this guy names it as one of the last breakthroughs, and if we are covering that subject today, I do believe that we are kind of running the state of the art here. So will there be new breakthroughs? Yes. And most probably, if I'm going to be lecturing this course in the following years, I hope so, I'll be adding new breakthroughs to my slides. But this is the newest one, and we are going to talk about it today, the transformers, the vision transformers specifically, but before the vision transformers, the transformers themselves. Okay, so actually we got ready for this. I mean, the last week we've been talking about attention, and when we were talking about attention, we talked about different models of attention. And when we were talking about different models of attention, we come to a point where we define the self-attention, a specific type of attention, which was not a recurrent type of attention, because the attention before self-attention was, if you remember, was something that was applied to recurrent encoder-decoder models. Remember? The relation between the decoder's hidden states to the encoder's previous hidden states altogether. I mean, if it's all hidden states of the encoder, it's global attention or local attention. You'll remember that. And the second type of attention we said was a type of attention transformers used. Now it's time to talk about transformers, because you kind of you already know the important fundamental architectures of the transformers, and we are going to look at the transformer architecture today, and we will understand it, and we will have the capacity to make comments about it. And I think transformers is a very nice architecture. Okay, and transformers, of course. I always thought about it. I mean, this is the second time I'm lecturing this course. I lectured this course before in another university, you know that already. I always thought about it. Why did they call this transformers? Because it's kind of funny. I mean, transformers is, already something in popular culture. And why did they, I mean, technically it doesn't make sense to me, because I'm coming from an electrical engineering background, and there is a device called transformers. It transforms, voltages to different levels of voltages. So why transformers? What is it transforming? If it is transforming sequences, why isn't it called sequencer, not a transformer? I finally have an idea about it, and I'm going to talk about it. Why it is not called a sequencer, but a transformer. We'll get there. So the idea of transformers is maybe the greatest booster of improvements in neural NLP today. Just like Hinton said, it is the most important breakthrough. The original paper is from 2017 by Vaswani, and it is called "Attention is All You Need." I love these guys when they name their papers, because they name it, so I mean, artistically, it is so many meanings hidden inside. Attention is all you need means you don't need recurrency, is trying to say, because in their model, they didn't have a recurrent connection at their encoder especially to handle the sequences. And at that time, this was something very new. You're telling the society of sequence modeling, who have been working on LSTMs and stuff to model languages till that day, and saying that, you've been using these LSTMs and recurrent neural networks. We don't need that, by the way. I'm using something else and it's working much better. Well, that's kind of a breakthrough. People kind of have a hard time accepting such a fact. So that's why it was an important paper. And again, it was Google's. I mean, for the last 5 years, almost all important studies are either by Google, mostly, and some by Facebook. So it is the state of the art in NLP. The famous GP3 transformer is actually a generative pre-trained transformer. That GPT's T is actually T. I'm sure you heard of GPT. You most probably read the article on Guardian, because recently, like 5 months ago, or half a year ago, in this year, the scientists worked on an article using GPT-3, and they asked, if we should be scared of artificial intelligence. And they've created, as far as I remember, 8 different outputs from GP3, and they've edited this. And in the end, they said, there's a note, if you read the article, go find and read it. There's an editor's note, and it says, well, we have run GPT-3 8 times to get an output for that question. Should we be scared of you, artificial intelligence? there were 8 different outputs, and we kind of edited them together. But this process was no different than editing a output of a human writer. So it was kind of same to us because we do that all the time. We do editing. We do edit the articles before we put to our journal, they said. And it was in Guardian, it was published. And it, people, the funny thing was, if you read it, if you haven't read it, please read it because it's so fun. It's in all the article, it's trying to say that, well, you shouldn't be afraid of me because I don't know, you're killing yourselves already. Why are you afraid of me? Kind of sentences. And then you read it, you're scared the hell out of it. Because it was so real. It was like mocking us. Of course I'm going to kill all of you, but I'm just mocking you kind of article. So please read it. It's just fantastic. The strength of this article actually came from the architecture, which was based on a transformer. That was the moral of the story. So transformers, but why? Just like I said, transformers was a breakthrough. And the intuition behind the transformers was increasing the capacity of parallelization. Because maybe the strongest bottleneck let me not put it strongest, maybe the bottleneck that was most difficult to overcome about the sequence modeling was you processed sequences, sequentially, one by one element by one element. This was something bad because, if it is a long sequence, it took longer to process it. And it made sense. We thought by then, we mean the scientific society, that was something natural to do. There was no other way to do it. However, these guys prove that there is a way to do it. And in the end, they've come up with something that was able to process all sequences, let's say sentences, regardless of their length, in parallel, in a fixed amount of computational time. So, compared to the recurrent neural networks, input and output sequences, sequential processing, this was a parallelized architecture. That was the intuition. So that was one of the answers. That's the first answer we should say to the question transformers, but why? So instead of a sequence operation, if you can do a matrix computation over the entire sentence, that would give you a head start if you're trying to do it fast, right? But that was not the only thing. That was not the only thing. Being parallel was the first thing that we are going to learn about this. So as we will see, the key concept of transformer architecture is that recurrent neural networks are completely removed and replaced by a particular kind of attention mechanism which runs in parallel. And this ability of transformers enormously increased the parallelization allowed to train bigger models, larger models, because if you make the sentence larger, although you have LSTMs which are kind of immune to vanishing gradients to handle larger dependencies, this will give you a better edge. Remember, when we were moving from vanilla RNN to LSTM, the idea was to be able to handle larger sequences. Yes, it did, but still there was a limit to it. Because in the end, LSTM's hidden state could keep some information. Then we had encoder-decoder, but that had a limit as well, because the encoder-decoder without the recurrent model of attention had this internal context vector. And as the sequence length, the sentence length got larger and larger, it was difficult to keep all the information in that context vector. Then came the recurrent model of attention, and it was limited as well, because you're trying to relate hidden states to decoder states. With transformers, we have the best when it comes to handling long-term dependencies. Actually, this is a statistic of GPT-3. GPT-3 from OpenAI holds about less than a quarter trillion parameters. Such models were unthinkable before transformers, okay? With LSTMs. Okay. Okay, let's continue. So, so before we get into the details of it, I'm going to first put the architecture. And we're going to go kind of from top to bottom approach. We're going to see the architecture, we're going to follow what's going on, and we are going to get into finer details of it then. So transformer architecture is highly parallel in nature. How? You feed an input to it. The input is tokenized words. So these are words. I mean, you construct a sentence. So each sentence is represented by tokens. When I say tokens, please note that it is just one-hot vectors. Because one-hot vectors being converted to vectors is the operation of embedding. And it's being handled by the transformer itself using an input embedding structure. I'm going to get into the details of input embedding whenever it's necessary. Don't worry about it. And when we have this input embedding, it's being fed to this multi-head attention mechanism. And it is also called self-attention because it's creating the attention out of these embeddings. You remember self-attention, right? We were using a vector itself to create attention, and we used three matrices, the key value and query matrices, right? Just forget about this. So there's this positional encoding here, which I'm going to be talking about in a couple of minutes. But imagine we don't have this. I mean, just let me get my pen to get your attention. Use my pen. Also, I love using my pen. Let me use my pen. So forget this. Just forget this. Imagine we don't have this. It's like this here for a moment. I'm feeding the vector, the entire sentence being converted to a set of vectors. So if this is a five sentence word with five word sentence, I'm sorry, 5 sentence or 5 word sentence with the dot in the end. With the dot in the end. And if my embedding size is k, which means each vector will be converted to k by 1 vectors, this is going to be 6 vectors of length k by 1. It's being sent to the self-attention mechanism we have seen the previous week, remember? And the thing about self-attention mechanism, you remember the thing about self-attention mechanism? It did not care about the order. When you feed something to self-attention mechanism, remember it from the previous week, you lose the order information. You created a context vector in the end, but you lost the order information. So actually the architecture, which is this part is the decoder, at first step loses the order of the sequence. That's pretty strange because, I mean, if you're trying to model sequences, that's a bit strange. But there's this positional encoding, of course, I've just covered it up for a moment. What I'm trying to say is, because you have this attention mechanism and you have a kind of residual connection here, like the resnets. You add this and normalize. Then you have a multi-layered perceptron here, fully connected layer. Again, add and normalize, which is kind of the encoder. And you have parallel n of these, like you have n of these guys in parallel. And in the end, you concatenate them. That's the encoder part. That's all you need to know about the encoder part. And if I'm going to get to the details of the encoder part, what I'm trying to say is, if you don't have this positional encoding, the encoder part of the transformer is actually not a sequence modeler. It is encoding a set of vectors. Because remember, a set of vectors being embedded like this and fed to a self-attention channel loses the order information. So it is not like a sequence, but a set. So the encoder, without this part, is actually encoding a set of vectors according to their relation between them, self-attention. That's why this transformer is not called a sequencer, by the way. But I'm going to get there. It was just an introduction. So the transformers architecture is highly parallel in nature, just like you see, we have parallel guys here, and I'm covering all the input all in once, so all parallel. It's compounded by an encoder and a decoder. We already started talking about the encoder. Both of them are made of the following blocks of sublayers, each represented n times in sequence, which means there are n parallel encoders and n parallel decoders, which are concatenated in the end. I'm going to get to the encoder, don't worry. And in the original model, how you feed the information is all inputs and outputs of the model sublayers and embedding layers have a dimension of 512. So if we start by the input, we feed a vector of a token sequence of 512 to here. Well, it is just like saying we always feed a sentence with 512 words exactly, but then we don't have 512 words in most sentences. I mean, we usually have less. Yes, you kind of pad 0 words in the end. I mean, you are going to send a sentence, I am happy, which is a 4 token sentence. I am happy, dots. Then what about, so 512 minus 4, which is 508. What about the, remaining 508 tokens? You feed not a word tokens there. You remember when we did this in the embedding, it was 0 padding. We didn't use these gradients. So whatever you feed this number. But it's also saying that you cannot feed a sentence with more than 512 words. Usually you don't have that, by the way. So it's like a limit. But that's the way it's designed. That's how it takes the same amount of time for every sentence it's being processed. This is something very important in the industry. In industry, it is not important that how long it takes, because you can just use better computers, better processors. If it's fixed amount of time for every sentence, that's the standard, and it can provide real-time operation, because real-time operation is by definition limited latency for the operation. Good. So let's delve into the embedding. So just like I said, if I didn't have these parts, the input being a token sequence fed to the input embedding, which made it a vector sequence, then self-attention and etc. will behave it not like, we'll treat the sequence not like a sequence, but a set, because we lose the order at the first block. Okay, then how I add the sequence ordering information? By positional encoding. That's one of the beauties of transformer. Transformer architecture ditches the recurrence mechanism in favor of multi-headed self-attention mechanism. So it doesn't use a recurrency like a feedback. It uses the self-attention block. So avoiding the RNN's method of recurrence results in massive speedup. And it theoretically can capture longer dependency in sentence. But when you do that, you lose the capacity to handle position sequence, the order of the sequence. Good. How to handle this? As each word in a sentence simultaneously flows through the transformer's encoder-decoder stack, the model itself doesn't have any sense of position order for each word. So these things doesn't have any sense of position order. Consequently, there is still the need of a way to incorporate the order of the words in our model. Yes, we are speaking a language. Sometimes you can change the order of the words, just like Yoda does in Star Wars. But in the end, there's a limit to it. So the order of the words is important for a language. So how do you do it? The architecture cannot handle it. How do you do it? And the answer is positional encoding. One possible solution, and it was the solution proposed in the paper, to give models some sense of order is to add a piece of information to the embedded vectors about its position. So you add an information to this vector set, it's a sequence of vectors, and you give it a sense of positional information. And how do you do that? How you do that is fantastic. Let's speculate on how to do that. I mean, you can speculate. I mean, you're all very good engineers or I'm scientists or computer scientists, statisticians. I don't know. You're coming from different backgrounds. But the first idea that comes to mind could be assigning a number to each time step between 0 and 1. So range in 0 means the first word is 0 and when 1 is the last time. So it is like I have a sentence of like I am happy with the dot token, it's 4. I put 0 for the first token. I put, so it's, let me write it. Let me write it. I am, I cannot write it. Happy dot. So it will be like, so this is token 0, token 1/3. I'm putting position informations, 2/3 and 1. Right? So good. Well, and you just kind of add that. So this already has a vector, right? This already had a vector. It was like it had a vector k dimensions, and you put it on top. So it becomes k plus 1 times 1. So you can, however, you're putting it on one dimension, and the rest of the vector dimension is not affected from it. And depending on how multi-attention handles it and the feed-forward neural network handles it, this vector dimension can get noisy and you may lose that information. I mean, the problem is that you cannot figure out how many words are so I'm going to get there. The first problem that comes to my mind is you can lose that information. I wish that there was a way to put the position information to the entire vector somehow, so that if one dimension of the vector is, noisy, I would still have the information in another dimension. And also, this what I just told you was the real reason, but there also we can say that one of the problems with that approach will be you can't figure out how many words are present in a specific range. So, you're putting some values in the range. Time step delta doesn't have a consistent meaning. In our forward sentence, time step delta changed by 1/3, right? But this doesn't have to necessarily be true for a word with a sentence with higher number of words, right? So, okay, it's difficult to handle. Still it can learn, but it's difficult to handle. More because the reason I just told you. We better put the entire information to the vector. How to do that? Another idea is to put numbers. So the first word 1, second word 2 to the vector. We still have that problem of putting this value to a single dimension, which is not good because still I could lose that dimension. What could be a better way to do it? Before that, the problem with this approach, another problem, the values get quite large. For a sentence with many words, you'll get things like 50, 51, and the network may have difficulty to make sense out of it. So what does 51 mean? A sentence with 51 words, does it make a difference when I'm trying to convert it? Well, it doesn't. Still, if you had a normalized way, if you could handle many things altogether with this positional encoding, that would be better. The first thing, you embed the positions to every dimension for the embedding vector, and you have a fixed delta that's been attached to it. Adding these values, you could add 1 to all values, you get 2 to all values. Well, that doesn't still make sense because for the first sentence, you'll be adding 1. For the last, for the first word, you'll be adding 1. For the last word, you'll be adding 50. You're changing the signal. You don't want to do that. You just want to add something to the vector, but you don't want to change the signal. You need something to be added, but still you need to have that information independently inside. Well, that's a difficult thing to do, but there's a way to do it. So let's go over the criteria that I'm talking about. It should output a unique encoding for each time step, where its position in a sentence. So we should understand which position the word is. Distance between any 2 time steps should be consistent. Yes. And our model should be able to generalize longer sentences without any efforts. Its values should be bounded. It must be deterministic. And I didn't write it here, but more important than all of these, it should be embedded in all dimensions, because one dimension could be noisy in this vector embedding. It should be there. And they've come up with this idea. And what is it? So the proposed encoding in the transforming design was a simple yet genius technique which satisfies all of those criteria. First of all, it's not a single number. It's embedded within the sequence, all the vectors. It's a d-dimensional vector. I mean, if d is the dimension of the embedding, I said k in this example, but let's say d, which contains information about a specific position. So it is like you're adding it here, right? So the input embedding comes. So if you have 4 words, I mean, in the end, you have 512 vectors, most of them being 0 vectors, like not a value vectors. You add positional encoding according to their positions, and you add them. So this is d-dimensional here, each token. And this is d-dimensional as well. You add them. But it's magical. You don't lose the embedding word information, and you don't lose the positional information. How do we do that? So this encode is integrated, summed up into the model itself. This vector is used to equip each word with information about its position in a sentence. In other words, we enhance the model's input embedding to inject the order of words. How? What we do is we add sine and cosine weights to it. So that's the formula. For each position, let t be the desired position here. So for desired position t. How we calculate this? We give sine times omega, a sine wave with frequency having omega times t, okay? Which means for each position, if I'm going to have sine a value, a frequency, for the next, I'm going to have sine times 2 times the frequency. And for the third one, I'm going to have a sine wave having a third times this frequency. If you're coming from signal processing background, you already know that. You don't have to know this in this course. I'm giving you the magic behind it. Sine waves with integer factors of frequency are orthogonal to each other. Orthogonal means in the space of sine waves, their inner product is 0, which means they cannot be confused with each other. Because being orthogonal is like x dimension and y dimension are orthogonal in the 3D space. When you move in the x dimension, nobody will think that you're moving in the y direction. They are orthogonal. That's the meaning of it. They are perpendicular in that n-dimensional space. For this example is 3-dimensional space. So you create a 512-dimensional space where each sine wave is orthogonal to each other, and you sum them up. Since they are orthogonal, these linear operations will not have much difficulty to differentiate their positions. And actually, this idea comes from the very famous idea of modulation in telecommunications engineering. So if you're coming from electrical engineering background, and if you have ever seen a telecommunication course, you know what modulation is, frequency modulation is. That's exactly frequency modulation. But since most people who are working on transformers and AI are coming from computer science background, people don't say this. I mean, but this is just frequency modulation. Because in frequency modulation, you create frequency envelopes where you embed this frequency formation very similar to this idea, so that you can listen to a certain frequency and you won't get confused with another frequency, because these frequencies having sine waves with frequencies of integer factors of each other are orthogonal. You can differentiate them easily. That's what this network does. So it can be derived from the definition. What you have is for the T1, so for the T, you have this information. So it's a d-dimensional vector. Or let's say T is 1. which is the first word, you add this. And for each dimension, we add another omega, and it changes for each dimension as well. As you can see, within the vector, the frequencies change slightly, not with an integer factor. But for PT1, this is the same as times t, so times 2. So it is pt plus 1. Let me write it, pt plus 1. So this is pt plus 1. My pen is not working correctly. Right, please write. This is again sine, please write. Omega 1, this is the same, but this is t plus 1. So this was, if t was 1, right, so it doesn't matter, it's t plus 1 times, this is a, sorry. So this makes this entire vector of sine waves orthogonal to this vector. When you add orthogonal components to other vectors, they can be separated from each other. And just like I said, this idea comes from telecommunications. This is analogous to telecommunications and signal processing, where frequency modulation is used to encode information in a carrier signal by varying the frequency of the wave with integer factors. Well, I repeat, this is not something you must learn. I mean, some of you are not coming from electrical engineering background, but this is what it is. Exactly, this is what it is. So this is something nice about this. I mean, the guys who have found transformers, they were a group in Google, and one of them was electrical engineer, and they were discussing this architecture, and they said, we need to find a way to encode the positions here. And the guy who has seen telecommunications simply said, why don't we do frequency modulation? And that was the best idea. So again, coming from different backgrounds is always an advantage, in my opinion. So this time it was electrical engineering. For another time, it could have been another, coming from mathematics might work, or computer science, whatever. Okay, so we know how the position is embedded. The rest of the network is, I mean, we already know the rest of the network. You have a set of tokens, sequence of tokens. You have an input embedding here, which is some linear layers embedding each token index to some vectors. You encode the positions, then you feed it to the multi-attention, which is self-attention. Remember, you have n number of these. Actually, in the original paper, there were 6 number of these. And with a residual connection, the output of the multi-attention, which is the context vector, is added to the vectors, input vectors, and they are normalized. And there's another layer, which is a residual block, kind of, because there's a residual connection and it's feed from the network. Add and norm. There you have your features out of the encoder. Strange. I mean, no, it is not recurrent. It looks like a simple artificial neural network. And it works fantastic, guys. So let's remember these blocks. Multi-head self-attention, a particular kind of attention. Self-attention, you already know this. It is called self-attention because both inputs of the alignment model, the model responsible for encoder hidden state weights, and even the components of the context vector are the same object. The self-attention, that's the story. I mean, because in normal attention, in the current model of attention, Badanaus, we related the hidden states of the decoder to the encoder, right? But in the self-attention, you're relating them, the attention of the embedded vectors to themselves, and without any specific knowledge of the position. Although position is encoded here. This is called multi-head because before applying attention, the inputs are linearly projected in 8 different spaces in parallel. I mean, actually it says 8, but in the original paper it's 6, maybe. It's a typo, I guess. So then we feed it to the fully connected feedback neural network. This is just the MLP, multi-layer perceptron, this artificial neural network. And they are added and normalized with themselves. Residual connection. That's it. That's the fantastic transformer encoder, and it's being used widely in many models, guys. no recurrent neural network. None. I mean, there's some sort of feedback in the decoder part we are going to talk about, but for the encoder, there is no recurrency. The key aspect is the self-attention. That's where you model the relation of the sequence. So differently from the RNN or CNN, it connects all positions with a constant number of sequentially executed and parallelizable operations. So it's like mapping each vector of the sequence to each of them. And creating a context vector. Well, the first question comes to this point as well. This is a sequence modeling course, and is it not an RNN course? Well, it's not. I mean, yes, RNNs were the tools that we used to model sequences until transformers came. They were the only tool, but they are not now. And it's kind of replacing RNNs for many applications, especially in NLP. Is it replacing every recurrent architecture? We don't know that yet. And it doesn't seem to be so, because there are some architectures where we need good old recurrent way of sequence modeling. We're going to discuss that. Is it better? Well, it is slightly better in their results, but more than it's better, it is efficient. That's why Amazon and Google use this encoder in their search. So it is not a sequence modeler, it's a transformer. Actually, without this positional encoding, it's a device to encode not sequences, to encode sets. So in future, imagine you have a machine learning problem, an artificial intelligence problem, where you're going to model not sequences, a set of values where the order is not important. You can apply transformers, but just cut the positional part. Just cut this part. It's going to be a transformer not for sequences, for sets. So for that matter, it is highly flexible as well. Okay, so before I finish this part, this hour, let me go over the self-attention mechanism that you already know. Self-attention created context vectors representing the relation of an individual token to the other tokens in the same sentence. Remember? So it is in this spirit that the majority of American girls, blah, 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 long sentence and padded. End of sentence, dot, and padded. This is a 512 vector, right? It goes on padding, goes on until the 512. So we calculate the context vector. How is it calculated? You already know this. You've seen it previously. I just said that I have 6 of these here, which means I have 6 different query key and value vectors which were learned during the training. I mean, how it's trained is another story, but the pre-trained transformer comes with 6 self-attention heads, each having 6 different key, query, and value matrices. So remember, if the key, query, and value matrices are different, the self-attention will create different context vectors. So it is like you are relating this sentence to sentence in, so let's think that these are the 6 dimensions of the self-attention. So this is self-attention 1, this is self-attention 2, self-attention 2, 3. So in this self-attention dimension, making is related to making. In this self-attention dimension, the word making is related to 2009. So maybe this dimension of self-attention model the context of time in the sentence. Maybe another model the context of space. Maybe another model the context of action. There are different dimensions of context in a sentence which can be represented by self-attention. Do we specifically know what each of these 6 self-attention blocks represent? No, they are transparent. Their definition of this context is abstract, but we don't have to. We don't have to. Because this is a neural network. We don't care about transparency in the first place. So that's what it does. That's why we have multi-head self-attention to represent different aspects of a sentence. So this was an example from I'm relating making 2009, and I said one of the dimensions is maybe related to time, but it doesn't necessarily have to be. I'm trying to give you an example to make it easy for you to understand. Most probably the abstract concepts these attention mechanisms differentiate and represent are things that are hard to put, in words. But in the end, they cover abstract relations that can be defined within the tokens of a sentence. That's what it does. That's why we have multiple. And in their tests, these guys, what do they, because this is a hyperparameter, you can increase this number, the amount of computation needed to increase that. What I guess is these guys tried n equals 3, n equals 5, n equals 10, and they've seen that after 6, their results do not change considerably. That's why they've chosen 6. Okay, so that was a good introduction to the encoder. Before I get to the decoder, I'm going to give a break, and before the break, I'm going to ask you if you have any questions.